Okay, this is session number 4, where we're gonna just talk a little bit about indication of tolerances. Let's start by this nice picture, where you see here you have a shaft here at the top, and then you have a hole here at the bottom. This is the starting point. And then we have what's called the basic size. The basic size, when we say, for example, the diameter of the shaft is 50 millimeter, or the diameter of the hole is 50 millimeters. So this is the basic size without considering any tolerances. So this is the size that we start with. So if you see this line here, which is like defining the basic size, so we start at the right end here, and then we say from the right end, which is like our constant edge, if you want, to the basic, to this line here, which is the distance between them defines the basic size. At this line here, we say this is our zero line, okay? Then any dimension that is lower than the basic size, we say it's going to be less than the basic size. So we identify this by negative. Any dimension that is higher than the basic line or crossing the basic line is going to be positive. What do I mean by that? If you just look at the shaft, for example, let's start by the shaft. So there is some tolerance here that would be given eventually. So we cannot exactly manufacture a shaft that exactly on the dot 50 millimeters. So we should give the manufacturer like some sort of limit, acceptable limit if you want. So we say that, okay, we can include, like, for example, plus or minus like 1 millimeter as the limit, or some sort of like that. So if, for example, if we have like 50 millimeter diameter and say we have a tolerance of plus or minus 1, so this means that if we, the inspector measures the diameter of the shaft and found it either 49 or 51, these two, or somewhere in between these two, should be acceptable. So let's go back to here. So we have the basic size, we have this line, zero line, and then you see if the minimum diameter of the shaft is less than the basic size, so we are on the negative side. So it means that the diameter of the shaft is eventually going to be less than the basic size. So the minimum diameter of the shaft is less than the basic size. And also if the maximum diameter of the shaft is on the left-hand side of this, so it means that the maximum diameter of the shaft is going to be less than the basic size, which means again that we are still less, either the minimum acceptable diameter or the maximum acceptable diameter is going to be less than the basic size. So for this, we have here kind of a tolerance zone. So this tolerance zone is like what is acceptable by us as a designer, and what we tell or communicate with the manufacturer that the acceptable limit. So there is what's called like upper deviation and lower deviation from the basic size. So for example, if this is the maximum size of the shaft, so the distance between here to here, which is the zero line or the basic size, is called the upper deviation. So where the cursor is here, so this is called the upper deviation. And between the minimum size here to the basic size, we have what's called the lower deviation. So this is what we define in our drawings: the upper deviation, the lower deviation from the basic size, the upper and lower acceptable deviation from the basic size. And you see here, the lower deviation goes with the minimum size, and the upper deviation goes with the maximum size. If you look at the bottom here, you will find that the hole here, both the minimum, if we start again from this edge and then measure the minimum diameter of the hole, it's on the right hand side, so it's on the positive side, so it's larger than the basic size. And then the maximum size of the hole as well is larger than the basic size, which means that both the minimum and the maximum dimensions of the hole are on the positive side. So again, the maximum size of the hole here goes with what's called the upper deviation. So the upper deviation is the difference between this line here, which is the maximum size, and the basic size. And the lower deviation here goes with the minimum size. So the minimum size goes with the lower deviation. So in this case, we have three types of what's called fitting. So if we were to fit this shaft to this hole, so there should be some sort of fitting between them. Are they going to be like loose when when we assemble them together? Are they going to be like difficult to assemble? So based on this kind of like assembling idea, we have three types of fittings. We have what's called clearance fit, we have transition fit, and then we have interference fit. So in order to kind of understand this table, which is quite important, we can think of that as three different fittings, how they fit together. Maybe the easier one to think about is the clearance fit. So the clearance fit means that there is like a bit of a clearance between the diameter of the hole and the diameter of the shaft. So here, this table is divided into three different parts. We have what's called clearance fits, we have transition fits, and then we have interference fits, okay? On the left-hand side here, you have the hole, which is shown by this hatching, and then you have the shaft, which is shown by this solid black rectangle. The rectangle here, the height of the rectangle here is considered as the clearance zone, which is like here, which is this area here, and this area here is the clearance zone for both the shaft and the hole. So this area here, the height of this hatched area identifies the clearance zone, okay, for the hole, and this height here identifies the clearance zone for the shaft. And you see here, you can just simply think about this as like these values can be changing. This hatched area could be on the left-hand side and the negative side, or it can expand and goes beyond that. It could be on the right-hand side, or it could be somewhere in between even, and the same applies for the hole. So see here, for example, if we think about this is the tolerance zone for the hole, and as we move in this direction, you see the height here is changing, okay, as we move in this direction, from clearance fit to transition fit to interference fit. And the same applies for the shaft. So as we move from here to here, the tolerance zone here changes, but not only changes but moves. What do I mean by that? If you look at the line here, which is the zero line that corresponds to this line here, as if just rotated everything 90 degrees in the 90 degrees in the clockwise direction. So you'll see that the bottom line here of the hole is always at the zero line. So meaning that this line here is like aligned with this line here. When this happens, when we have the lower deviation of the hole is equal to zero, so meaning that this line here aligns with the size, so we have what's called the hole base tolerance system. Because we can also have a shaft base tolerance system if this line here coincides or aligns with this basic size line. But in this case, what you see on the screen here, just if you look at these hatched areas, which corresponds to the hole, and the lower deviation here is zero, It is also, if you focus here, you see that this this value is 0, this value is 0, 0, 0, 0, 0, 0, means that the lower deviation here of the hole is 0, and we are seeing here the table for a hole-based tolerance system. So the minimum and the maximum, or the upper and the lower deviation of the shaft changes and also moves, meaning that it becomes closer to the zero line. To the extent at some point here, it coincides with the zero line, and even it goes above the zero line. Means that just imagine that you are expanding the minimum and the maximum values here, and then this hatched area keeps moving to the left, and at some point it goes beyond this line. Just imagine that this area is moving in this direction, and you will just understand how it simulates here. So normally they give this kind of fits, they give it numbers. So capital letters goes with the whole, if we are dealing with a whole based system, and small letters goes with the shaft, okay? So for example, if we pick the first one, you see we have H capital here 11 and C11, small c11 for the shaft, capital H 11 for the hole. On the left-hand side here, it gives you some range of the basic size. So basic size here, for example, above 0 and below 3 millimeters. So this gives you the size of the hole that, or the set of the range of holes that you can deal with. So if we pick the first one, which is the clearance fit, H capital and C11, see here for the H11, that is, it shows the upper and the lower deviation of the hole. You have, if we take the first row only and the first column, we have 4 numbers here. We have 60, 0, we have 60, and 120. For the H, the capital H11, we have a plus sign, meaning that these two numbers are positive, so on this side. And C11 has a negative sign, which means that they are both on the left-hand side of the line. And then we have 60 and 120, meaning that so the upper deviation is 60 and the lower deviation is 120. And here for the hole, the upper deviation is 60, which is like from here, from this line to the basic line, is 60, and the lower deviation is 0, meaning that this line and this line, they coincide together, they align to one another. And these values are defined as in micrometers, okay? So if you just imagine to draw this here, it will be something similar. So the shaft is not going to change. It will be on the left-hand side, but the only change here, if you just imagine that this line and this line, they coincide together, and this area here defines the tolerance area, and this hatched line here defines the tolerance zone for the shaft. Still, there is like a clearance between them because this one is not touching this one, so there is a clearance here. And then when you fit these two together, even after this line coincides with this line, there is a clearance between the maximum value for the diameter of the shaft and the basic line, which means that we have a clearance fit. So they have a clearance between them. That's why it's shown here that a little bit away from one another, meaning that there is a clearance. And this clearance keeps decreasing as you move in this direction. At some point here, they become like, we start the transition fit, and then the shaft here dimensions, they move to the left-hand side and becomes even higher than the clearance for the shaft for the hole. So here we have interference fit, meaning that the diameter of the shaft is higher than or larger than the diameter of the hole, and this is what's called the interference fit. You need to read a little bit more about this. You need to just have a look on the numbers and the tables and to try to make sense of this. but this is just kind of a basic idea of the clearance fit, transition fit, interference fit, and the hole-based system, the shaft-based system, and what do you expect when you see these numbers? Remember when we were just showing the dimensions for the threads, it was given like some sort of numbers like G6 or something like that. So this is where you can get the upper limit and the lower limit for the deviation or the tolerance. You get it from these kind of tables based on the diameters, the nominal diameters or the basic diameter. So depending on the field of application, you have the tolerances that applies to the dimensions can be indicated by three methods. One is called limit deviations. The second is called limits of dimension, and the third is called general tolerances. They all serve the same function, but the way we present it on the drawings is different. So the limit deviations, for example, you have like it's expressed in the same dimensions as the main dimensional value, and then you put the upper deviation above the lower deviation, something similar to this. So the basic size is 30, and here you have the upper deviation, which is +1. +1 means that it's on the left-hand side of this line, zero line, if you remember. -2 means that it's on the right-hand side of this zero line. So in here, the maximum and the minimum deviation is, on the left and the right-hand sides of the zero line. If one of them is zero, similar to the hole-based system where the minimum deviation or the lower deviation was zero and the lines were identical, so you still need to include this, saying that 30 is your basic size, 0 is the upper deviation, and -2,5 is, or 2.5 is the minimum deviation. They all here, they have the same unit. So if this is 30 is millimeters, so it's +1 mil, -2 mil. Okay. If the tolerance is symmetrical, so you have like on the plus side and on the negative side, they are the same. So you can just add it to the dimensions like this, 30 plus or minus 1. This is where the hatched area is in the middle, or the zero line is in the middle of the hatched area, where part of it on the left-hand side, part of it on the right-hand side, it is shown like symmetrical like this. The limit dimension or limits of dimensions, you here identify the maximum and the minimum dimensions of the shaft or the hole. So the larger dimensions are placed above the minimum dimension, something similar to this. So you just, as if you are adding the tolerance to the dimension itself. So it says here the upper dimension is 32.198 and the lower dimension is 32.195. This is the way, another method of including the tolerances to your dimensions. The third one is general tolerances. When the tolerances applies for example, for all the dimensions in the drawings, you can just say, for example, you write a note, you don't need to add it to each and every dimension. You can say tolerances except where otherwise stated is plus or minus x, which is like x replaced by the value that you think it's correct for your drawings. For example, you could say also tolerance on cast thickness plus or minus x% and replace x by a number, or you can include a table and say like sizes up to this value, we should apply this tolerance value between this dimension to this dimension, apply this tolerance between this dimension to this dimension, apply this tolerance on angles, for example, apply this tolerance. So these are kind of general tolerances that you can include in your drawings as a notes. Or for tolerance of forging dimensions, you can refer to a specific standard as well. That's the end of session number 4.